Or did I give you that straight definition? Didn't ask you to fill out anything? Oh, yeah, darn. Okay, when matter changes from one state to another, we talked about the 3 states, right? What are they?
Solid, liquid, and gas.
Well, you went reverse, didn't you? Most times people start with the solid, but you went reverse and tripped everybody up. Okay? From one state to another, especially when 2 or more states are present at the same time. Believe it or not, if during a phase change, all the way through the phase change, you will have 2 phases at once. Like if you take an ice cube and start melting it, you have some of it's liquid and some of it's what? Solid. Okay? Alright, so here's what's really happening. What causes these phase change? Before we can get into too much about the phase changes, we got to define temperature. What's temperature? I mean, the definition is right off the board, so at the very least. Okay, so it's essentially average thermal energy. It's actually not the best definition of it. What does it say in your vocab sheet?
The average thermal energy of a substance furnace.
It's true, but how many? So underneath thermal energy in brackets, I want you to put kinetic energy. Okay, because that's going to make a little bit more sense. The subtlety is not a big difference, but so what's up there isn't wrong. It's just I gotta define what thermal energy is. Yes. So like what I would do in the notes that you're given, like right underneath where it says thermal, like kinetic, just because you guys know from our definition of kinetic energy. Did we define kinetic energy? Yeah. We didn't define it, but we talked about it, right?
Yeah.
What is kinetic energy? I can't spell.
Yeah.
I seriously, guys. I'll go on a rant at one point sometime during this year about how your education matters and how if you cut corners, it really affects your future. And for me, it caused me to lose thousands of dollars in scholarship. Because on the ACT, I got 30 and above on math and science. You want to know how I did on English and reading?
Like Joe?
Pretty much. So I got over 30 on both math and science, and my ACT score was a 22. What does that tell you about what my English and reading was? Really low. Okay? And a lot of times colleges will give you money based on your ACT score. Usually if you get above a 27 on your ACT, you should get what's called a presidential scholarship, which is one of the close to the highest amount they give you. So we're talking I probably lost out about $7,000, $8,000 a year in scholarship money. Okay, so you don't think your education's important? Yeah, $1,000 is, you're not really unsure with what that seems like a lot. You may not know exactly because you don't deal with money, but it's a lot of money. Thankfully, I got like $15,000 a year in athletic scholarships, so that helped. But I could have gotten both. All right. So let's define this. Temperature is basically the average of your movement. That's what kinetic means, right? Energy in motion. Okay, so if I've got a beaker of water and I put a thermometer in there, what I'm essentially measuring is how fast those particles are moving. Now, the reason why it's average is because you think all the particles are exactly perfectly moving at the same exact speed. No, they're not. They're not all moving at the exact perfect speed. Okay? There are some particles that are moving slightly faster than others, And those particles tend to go to the surface, and that's where the process of evaporation we'll get to later happens at the surface, and that's where the faster particles go to. Okay? So, when the speed of the vibrations of the particles increases, we see an increase in temperature. And we said when we dealt with the three phase changes, or three phases, excuse me, they all had something to do with kinetic energy, correct? We should probably review. Which one has the least amount of kinetic energy? Solid. What does that mean? When I say least amount of kinetic energy, explain that in something that makes sense. It's moving the least amount. Does that make sense? Okay? Which one has the most kinetic energy? Gases. Well, this just simply means what? It's moving faster. Remember we talked about the reason why gas particles break away from each other? Because they have enough speed now to overcome the forces that were holding them together. Like, for example, and I may or may not have used this example. Have you ever taken two magnets and went really fast by each other?
Yeah.
Do you notice anything? If you take two magnets and really fast and go by each other, you don't notice anything. Because they're moving so fast that even though they're still attracted, right, these two magnets are still attracted, because they're moving so fast, it's a negligible attraction. Okay? So, very important that kinetic energy is very closely related to temperature. Okay? And we know that temperature changes usually is how we get our phase changes. Yes? Okay? If I put an ice cube out in room temperature, there's a difference in temperature, and that results in a phase change eventually. Alright, this is something that probably you will not get until I explain it. Okay? It says, while the substance is changing phase, the temperature what? Oh. Okay, so temperature, by definition, is the average kinetic energy. So if during a phase change, the average kinetic energy isn't changing, where is the energy going? If it's not going to change the temperature, it's got to go somewhere, because last time I checked, when you put a pot of water on the stove and you boil it, you're still adding energy, aren't you? While it's boiling, you still are adding energy. Where is that energy going? Because if you put a thermometer into the boiling water, the temperature stays the same the whole time, even though you're still adding energy. Anyone know what that temperature is? What is the temperature of boiling for water? In Celsius. I'll make it easier. 100 degrees. Okay, so if I sat here and boiled water and put a thermometer in it, it would stay at 100 degrees over time. But you're still adding energy, right? So where's the energy going? Yes? All right.
So about the thing where the magnets, you're going so fast that the force can't hold it together. So if you were able to go fast enough, does that mean that you could go past the force keeping together time and space?
That is a loaded question. I do not know the answer to that one. In theory, yes, but that is strictly theory. But again, that's more of a philosophical question than it is a science question, because that's assuming you could get to that speed, which is probably not possible. So it's philosophy and science put together. You see what I'm saying? It's not just a science question. Okay? Here's the answer to where the energy goes. In fact, I'm going to show you kind of what I would call a phase diagram. We'll talk much more about this later. Let's say this is time, and we're adding, and you don't have to put this in your notes. I'm just going, again, I'm kind of going deeper than I probably need to. You're adding energy at a constant. Let's just say we'll add -10, 0. Holy, 41 already?
Yeah.
I am not doing that. Oh man! Okay, sorry, I won't show you that. I won't go above and beyond. Okay? So, I'm still adding energy, but that energy isn't making the speed of the particles go up. It's going into or out of the bonds, causing it to change phases. So what you'll see is the temperature will, assuming let's say we got solid ice. Okay? You add energy, the temperature goes up until you reach the melting point of the ice. Then it stays constant until all the ice is melted. Because you're breaking in this case, yeah, you're breaking the bonds that are holding it as a solid. As soon as it's all been broken, the temperature rises until you reach the boiling point. Then the temperature stays the same while it's boiling. This is why they say steam is more dangerous than putting your hand in boiling water. Why? Why is it more dangerous to expose yourself to steam, gas, or vapor water than it is to just put your hand in boiling water? What's the hottest you can get in boiling water? 100 degrees. Can't get any hotter. Put steam, the least it could be is what? 100 degrees. It has the ability to get a lot hotter than that. Okay? Yes. Because during the phase change, no temperature changes. Only after it's been converted completely to gas do you notice a temperature change. Alright, I'm not going to go crazy into this. Okay, it says occurs when enough heat is added to allow the particles to have enough energy to match the attractive forces between them. So essentially, we said solid has low energy, right? Okay, so a melting is going from a solid to a liquid. So I have to increase the energy, right? Okay? That causes melting. I'm going to go through this kind of quickly. Okay? At the melting point, the particles can flow over one another because now we've got the ability to flow. What is a liquid also known as? A fluid. Okay, good. Freezing. No, notice this. This is important. Did you know freezing and melting happen at the same temperature? If you think about it, you'll agree. But freezing and melting happen at the same temperature. Anybody know what it is for water? It's Celsius. If someone's telling you in Celsius? 0 degrees. When does water freeze? You guys want to do Fahrenheit? Let's do Fahrenheit. When does water freeze? When does water melt?
Nope. Really hot.
32 degrees. Water freezes at 32 degrees. Water melts at 32 degrees. You know what we're going to probably have to do today? Here's what we're going to do. We're not going to finish all this today. We're going to omit the lab. We still have a test on Friday. I'll figure it out. But we're not going to finish this today because we only have 4 more minutes. I cannot. Did you guys sit up in the hallway like really long?
Yeah. 10 minutes.
10 minutes?
No. We came in at like 11 minutes.
Okay, all right. Okay. I do want to hit this. I want to make sure this makes sense. Okay? I am gonna draw that curve. We're not gonna finish it. Energy added over time. Because essentially our lab would just be doing this, which, yeah, melting and freezing things is cool, but you guys have seen that quite a bit, yeah? Seen things melt at degrees. What'd you say?
Ice maker doesn't work.
No homework.
Yay!
Oh, don't pack stuff up yet, though.
Oh, we don't
All right. is what a heating curve for water looks like. Where do you notice no temperature change? What's the temperature?
0 degrees. Is that Celsius?
This is Celsius, yes. So water freezes and melts at 0 degrees Celsius. Water boils or evaporates and condenses at the same temperature. What is it? Notice, look at this graph. I know we struggle with graphical interpretation. This is why typically science on the ACT kids struggle with, because you don't know how to interpret a graph. Look at it. This is temperature, right?
Yeah.
What do we say doesn't happen during a phase change? Temperature doesn't change during a phase change. Where's the only 2 locations on the graph where the temperature does not change?
Freezing and boiling.
Where it melts and freezes, where it boils or condenses. Now listen, I want to show you something. Could I start at -10 and add energy?
Yeah.
It would melt, increase, boil, increase. Could I go the other direction? Could I take energy away from gas? Gas would lose energy, condense, lose energy, freeze, get colder. What? For example, and we haven't defined this yet, but most of the kids, believe it or not, there's water on the outside of this glass. A lot of kids think that the water from inside the glass goes through the glass. Where does it come from? How old are these people? I'm serious. Where does the water come from? Why touch it? Is there water on the outside? You feel that? There's water on the outside. Where did it come from? From the air has water in it. The air comes in contact with my really cold cup. So hot gas hits cold cup. What does it do? Energy gets transferred to the cup, and the speed of the gas slows down so that it what? Turns into a liquid. Water did not go from in the cup, through the cup, to the outside of the cup. Gas hit the cup, transferred energy, cooled it down enough that it turned into a liquid from the gas state. That's called condensing. We'll talk more about this tomorrow. No work.
It's time for
We didn't finish. No work.
I love that.
That's not good. Naki, don't say that.
How was science?
We didn't finish the note.
Why don't you not go through the cup? In the cup and through the cup. So again, that's what I
Did you turn the camera off?
I actually had no clue. My entire day was thrown off by this laser. So confused. I expect you to. Oh, that's all. That worked.
Abby? I'm not. Okay, whatever you say. Abby, wait for me. It's the same problem.
He's getting shipped.